Okay, so today we will import BERT from Hugging Face library and train it on classification task. So you don't need to submit this notebook, but it will help you for the new homework, which I will upload a little bit later today. And yeah, let's try to open this in Kaggle. Just how it works. So new notebook, and I believe here, yes, here you can import notebook or import, yep, and from GitHub. And it will upload this notebook. Um, then you can change settings to GPU. And if, yeah, so um,
How did you get the GPU?
in settings, accelerator.
Do you have to pay for that? Mine's
No,
free now.
no, it's yeah. So it provides 30 GPU hours per week for free. So that's why I want to show you how to use it. So you have more than enough time for homeworks. So I I believe the Transformers library is installed, so we don't. Oh, wait a second. We don't need to install it, I believe. Um, okay, default installing, and it connects to the GPU, I believe. Yeah, so here you can see your GPU. For example, I used GPU yesterday for homework, uh, 5, uh, and now I have 12 hours. You should have 30 hours. So yeah, the most popular library for large language models is transformers from Hugging Face. Of course, you can train your own transformer, but we will use pre-trained mostly. And in this library, there is pipeline. It's kind of often a scikit-learn when you can stack different modules. So we will use pipeline. And in this pipeline, you can indicate the task which you want to work with. And it will choose by default a model that was trained on this specific task. So you can indicate model. If you don't indicate it, it will choose a model from Hugging Face. So for example, here we create a pipeline for sentiment analysis. And to apply model, you just type classifier and then the string, and it will provide the classification. So first it should upload the model. Yeah, so it uploads the model. And after it uploaded the model, you will see the output result. It's a dictionary with label and score. So label is the word sentiment label, and score is the probability. So this is how you can use pre-trained models easily. Yeah, so this was the code for the kind of part of homework solution, but I won't ask you to submit this notebook. It's just to classify which the house of from Game of Thrones is kind of good or bad based on their um, uh, what is called their credo, their what is the word for this logo or how it's called, kind of yeah. So the phrase that classify kind of that they pronounced every time when they met together. What is the word?
Motto or slogan?
Slogan, yeah. um, like something which is dead can't be dead, or something like that. So the easiest way, so let's just classify, for example, barations. So how to apply our model to this barations slogan. So we just should write classifier of this phrase, and that's it. Oops. And it will provide the classification. Maybe because of the word fury, it classifies as negative. Okay, so let's recall which tasks BERT was trained on. Do you remember there were two parts of loss function? One part was applied to CLS token, classified the first token. The other part was used several tokens, 15% of tokens from the model, from the input. So do you remember which tasks each loss actually function was solving? So in BERT model, we had two parts of loss function, loss 1 and loss 2. So the second part was applied to the task which is called MLM, and the first part was applied to CLS token. So do you remember which tasks actually BERT was trained on? So next, yeah, the second one, masked language model, was for the words which were replaced, masked, or unchanged. And the first part, do you remember? The input was 2 sentences, and the goal was to classify if these sentences are consequent or they are not related. So this task is called next sentence prediction. Next sentence prediction. So now, because we know that one of the tasks was a masked language model, let's play with that, and let's cover some tokens with mask token. So in the next code, we will import another language model with task fill mask. So, and we will use very old model BERT based on case. Let's read the mask index from model tokenizer and save this in our variable mask and apply this to the following phrase, Donald, then the token mask is the president of the United States, and apply this model for this phrase. So it uploads again model first, and then returns 5 top results. So the first result, mask is replaced with Trump, and the probability is 99%. Then it has other tokens, but with very small probability. And because it's BERT uncased, if you would use case-sensitive model, then you wouldn't see the other results on the second place, like duck or Ross, because it would actually take into account the name. Okay. Okay, so let's now try to apply our model. So, but not for the question when the Soviet Union was founded, but for example, when the United States were founded. So how to use mask token to answer to force BERT answer the question which year the United States were founded. Can you suggest the prompt? Yes.
The United States was founded in math.
Yes, it's um, because it's not GPT model, we can't just ask a question. This model was trained to predict the mask token, so we can type and because it's low case uncased, I can just use low case. The United States founded in mask. And let's see the result. So the first most probable it's column. So we can add the period after mask. So maybe it will catch more context. Okay, it was founded in C. It was founded in Europe. It was founded in Canada. And it was founded in America. So, and I think because this model was trained on some tests, maybe C comes from possible answers from tests, A, B, C. So maybe we can add year in the year.
C.
Well, yeah, but now it produces some numbers, but they're all wrong. Well, but you shouldn't expect like accurate results because um, this was trained on Wikipedia and not only on the historical date history, but also on the literature. So it kind of learned all possible contexts. But at least this is just to give you an idea how we can use language model to answer some questions. Actually, maybe we can force it in the mask century. In the 19th century, no. Well, but at least in this case, we have one of the correct answers. And what is the correct answer in which century the United States were founded?
I think 18.
Yeah, so at least we have one correct answer in this top 5. And this is the typical situation. We have correct tokens typically in top 10, 5 answers of the model. And also, this is another reason why it's not a good idea to use always the token with highest probability. Okay, so now let's look at another task, which is called named entity recognition, or NER, named entity recognition. So let's write the code. So what should I write here? How to call a model for this task, named entity recognition. Pipeline, uh, like the same that we had here. um, transformer pipeline, sorry, transformer pipeline. And here, NER. So it will upload some model by default, and so it chooses BERT large cased fine-tuned on con LL, which was the popular competition, and they provided their data set. That's why it's called call LL. So this is the data set on which it was trained. So it uploads the model, it uploads the tokenizer. Different models use different tokenizers. So we should use tokenizer for the model that we're using. And let's print this output that was applied to this text. Um, so this is the output. And you can see here like person, location, tags, but also miscellaneous. And let's think about this word. What is that ta? You can look at the original text and compare. So named entity recognition, it kind of labels the named entities. So what is that ta miscellaneous? Yes, it's BP byte pair encoding in practice. Um, so it's actually Rosetta, but it was because there wasn't such word in the dictionary, it was split into two parts. And it wasn't recognized as a person as it should be. It just was recognized as miscellaneous. But in Hugging Face, you can find better models trained on this task named entity recognition that will actually take care of these splits and will return Rosetta instead of Tita. Okay, so yeah, let's look more closely at tokenizer and building blocks of this Hugging Face library. So in this code, I import BERT based on case from pre-trained. And also I import the tokenizer for this model. Well, when you will do homework, you will use some model from Hugging Face, and if you apply tokenizer, you will see that some models has index 101 for CLS token. Some models will have index 1 for CLS token. So we should use the same tokenizer that was used for training the model that we are using. So let's look at these two lines and apply tokenizer to these lines and print the result. So we had batch with two lines. Luke, I'm your father. And this is, oh, by the way, it's important that in tokenizer you indicate these parameters. So the first parameter, padding true, will pad your sentences to the longest sentence in the batch. If you don't indicate padding true, you will get an error. Because, and the error will say that that your tensors are of different lengths. Then truncation through nobody asked me about what is the maximum length, input length to language models. So the this model like from 2019, an old one, it has the maximum length 512 tokens. So it's about half of page. And if you pass longer phrases, again, you will get an error. What is that error? Like in the index error that indexes outside of the largest available size. So this is truncation. And return tensors, can you guess what is this parameter? Stands for return tensors PT. So if I'm not using that, it will return the dictionary of string of lists. But if we use return tensors PT, it will return tensors in PyTorch format. You could return in TensorFlow TF. So we return this as tensors. And as you can imagine, this first index stands for CLS token. So it kind of adds CLS token under the hood to our input. Also, it adds separator and padding. So, and also it creates attention with zeros on the position of paddings. So this is the output from the BERT model. From the tokenizer, sorry, from tokenizer of this model. And decode will decode the tokenized sentences, so you can see which tokens were added to the input. Okay, now let's try to train this model. And for example, I want that this model returns high probability for the first phrase and low probability for the second phrase. I mean, it's just a made-up example. So how to fine-tune BERT model to classify like the first line as positive and the second line as negative. So let's get the embedding of this phrase first. So in BERT model, there is a layer which is called Pooler output. And I will explain now. And if you apply your model to the input batch, this layer, Pooler output, will return the embedding of CLS token, of the first token. And let's look at these models. So let's open Hugging Face. And oh no, actually, yeah, in Hugging Face you can just search for models. But I want to open this BERT uncased. Hugging Face BERT GitHub. Because it's open access library, you can always look at the code inside. So here is BERT. So transformers library. Then in model, you can choose BERT, and model in BERT contains actually the code. Let's look at the Pooler. BERT Pooler output. And you can see here that Pooler output takes the first token with index 0, which actually corresponds to CLS token. And after that, it applies a linear layer to this embedding and activation. And this is the output from this Pooler output layer. So Pooler output layer is not just the embedding of CLS token, it's embedding, but after a linear layer applied to this embedding. In GPT model, they use the last token instead of the first one because it's a different model. But this is how you can get the embedding of the sentence. For example, if you want to compare two sentences, you can just get embeddings from BERT and calculate cosine similarity. As you remember, in first week, we tried to create embedding of the sentence based on word embeddings. Yeah, now you have much better tool. Okay. Now let's, we have just few minutes left. I wanted to train this model. So we can create the model, my BERT, from NNN module. Init. Let's see if we don't have time. We can continue next time. Init. Of self. And here super. Wait a second. Yes, super. Init. Just inherit from our module class. Then we initialize model self BERT. It's our model. And because we want to use binary classification, we should reduce the output shape from Euler output to the size of 1 or 2. So we will use linear layer self dot classify, which will be linear. What is the shape of this output? $768. 2, 2. And then we define model forward. Forward of batch. And actually we can use keywords here instead of passing the that all these elements, we can use keywords. Okay. So apply our BERT model. And we apply linear layer. Okay, what's wrong? Self return. So let's initialize our model. And we can look at the output. For example, my model of our input phrase. Backwards and forwards. Oh, I made a misprint. CL classifier. Or something else. Input must be a tensor. Okay, I think we should stop now because it looks, yeah, we should go back. So the idea is that in the output, you would get just two numbers, probabilities. And after that, we can apply gradient descent and train this BERT model to predict the first sentence as positive and the second sentence as negative. But we will continue this next time because we should. Oh, wait a second. We have time till 50. Okay, maybe we can at least fix these errors. So what is the error here? Input must be a tensor, not base model output. Okay. Because we should use a Puller output here. The output from BERT is the dictionary, and we will take Puller out. Puller output. Put. Okay, and now we have these numbers. And actually, because we have 2 minutes more left, we actually can train. So let's call optimizer torch optim Adam of my model parameters. And we can calculate output. So logits will be the output from my model. Then we can calculate loss. Entropy between logits, output from my model, and some labels that I just made up. Torch tensor of positive, negative, and F loss equals. And finally, we can do loss backward. Backward. And before backward, we should zero gradients, optimizer zero grad. And optimizer step, optimizer step, and print loss, print loss dot item. Let's run it. And oh, I didn't. So if I run it again, the loss should go down, but It doesn't because this model has the dropout, so it's very noisy in the and we can actually um, kind of cancel dropout if we use my model dot train false. It will my model. It will print the model, but also it will freeze the dropout. And if we run now, the loss should go down. Yeah, it goes down. So yeah, that's it for today. Sorry, it took a little bit longer, but now at least you understand how to force language model to do something that you want from this model. Okay, stop sharing.
If anybody's wondering how to use the Kaggle GPU, you just have to add a phone number to your account